So in this video, we're going to take a look at how to do some operations on our vector value functions, particularly differentiation and integration. Now, we're going to start with differentiation because it's a little bit easier than integration. So let's define our vector value function r of t as f at ti plus g at tj plus h at tk, where f, g, and h are differentiable. Then the derivative is just going to be the derivative of each of those functions that comprise r of t. So in other words, r prime of t is f prime of t, g prime of t, h prime of t times ijk. If you want to take a higher order derivative, you just do the second and third and fourth derivatives, just like you would with the first derivative. We say that r of t is smooth if the derivatives are continuous on that interval. All right, so basically that means you could take the derivative and there's no places to where you're going to it's going to be non-zero for the derivative and in the domain. If there is a point to where the vector value function does equal the zero vector, that's called a cusp or a node. All right? So let's take a look at a few examples of this. So for each of the vector value functions, we're going to find the derivative, r prime of t, and then we're going to determine the intervals where r of t is smooth. All right, so let's go back to Calculus 1, and we're going to remember some of the rules that are necessary for us to be able to find the derivatives of these functions. All right, so remember with radical functions, the first thing you probably want to do is you want to rewrite this. Okay, so let's just rewrite r of t as t to the 1/2 I plus 1 minus t cubed j minus tk. Right? And from there, what we can do is we can just find the derivative of each of those expressions as the coefficients. So r prime of t is going to be equal to 1/2 t to the minus 1/2 I minus 3t squared j minus 1k. Okay. Or another way to write this would be 1 over 2 roots of t I minus 3t squared j minus k. All right, so that's our derivative. And then the other part of the question is, where is this smooth? Well, there's not necessarily a number that I can plug in to get to the zero vector, because right here, this is always going to be a constant. All right, so no matter what I plug in for t, I'm always going to end up with at least a negative k. All right. However, we do notice that there are some domain restrictions on the continuity because of this. All right, so we could say that r is smooth whenever t is greater than 0, because we can't have 0 in a denominator and we can't have anything less than 0 under a radical. So r is smooth from 0 to infinity. All right? So essentially what we're doing is we're just figuring out where the derivative is continuous. A second example. So we have this e to the minus t plus t squared plus tan of t. All right? So r prime of t is going to be equal to e to the minus ti, right? So remember, the derivative of e to any power is e, but then we have a chain rule. So by our chain rule, we're going to multiply that by -1. All right, so the derivative of negative t is -1. All right, derivative of t squared, that one's pretty easy. That's 2t j, and then derivative of tangent, that's one you'd have to memorize. That's your secant square of t times k. All right, so the question is, where is r of t, r prime of t, continuous to make it smooth? All right, and are there any cusps or nodes? Well, it doesn't look like that there's any number that we could plug in to get 0 for all of these. All right, so there's not going to be any cusps or nodes. The -1 e to the minus t, that's continuous everywhere. All right, so we don't even have to worry about that. All right, because the domain of that's all real numbers. The domain of 2t is all real numbers, but the secant square is a problem. All right? it might be helpful to think of secant square as 1 over cos square of t. And we know that cosine is equal to 0 at pi halves, 3 pi halves, 5 pi halves, etc. All right, so in fact, that's the domain of the tangent of t. All right, pi halves, 3 pi halves, 5 pi halves. So it's not necessarily too shocking that when we find the derivative, the domain of the derivative is similar to that. All right, so we know that t cannot be equal to pi halves, 3 pi halves, 5 pi halves, etc. All right, so what we can say is that t is going to be smooth. So we're going to say t, or r, excuse me, is smooth over the interval pi half or dot 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 union pi halves, 3 pi halves, union 3 pi halves, 5 pi halves, union dot dot dot. Right. So that's how we're going to go ahead and take care of derivatives of these vector value functions. We take the derivative and then we determine where it's differentiable, basically where it's continuous, the derivative is. And wherever it's continuous, that means that it's smooth over that interval. All right, so there are some properties of vector value functions with respect to the derivative. And when we're starting to take the derivative of sums, differences, dots, and crosses, all right, that's where we're going to start utilizing some of these rules. Okay, so let's just take a look at each of these, and none of them are going to be too surprising because they follow the regular rules of derivatives. So for instance, if we take the derivative of a constant times a vector value function, the constant just comes out front and we take the derivative. Derivatives of sum and differences is distributable. Okay, so we could just say the sum of the derivatives would be the derivative of the sum. All right. We're going to implement a product rule. So if we have two vector functions, we can just use the product rule, fg prime plus f prime g, except it would be w r prime plus w prime r. The same thing's true with the dot product. So if we have the derivative of a dot, then we just take the derivative of each of those, each of the dots, and then we go through and just implement the product rule that way. Same thing with the product rule of a cross product. All right, so we take the derivative of the second, multiply it by, or take the cross of the first, and to that we add the derivative of the first crossed with the second. There's a chain rule. You wouldn't be surprised that if you have a function inside of a function, that you just find the derivative of that. We just saw that. And then finally, if the dot product of two functions is equal to a constant, then r of t dot r prime of t is 0. All right. So let's go through and just maybe evaluate some of these. All right. So let's define r as 1 over t plus negative j plus ln t of k, and then u is t squared minus 2t plus k. All right. So if we wanted to find the derivative of the dot product, now certainly we could find the dot product and then take the derivative, or we could just find r prime of t, and r prime of t, we have to think of 1 over t as t to the minus 1, so that's going to be negative t to the minus 2i. The derivative of negative 1 is just going to be nothing, so I'm just going to say minus 0j. And the derivative of ln is 1 over whatever's inside of there, k. Right? Or another way to write this would be the opposite of 1 over t squared I plus 1 over t k. And then u prime of t is going to be equal to, really easily, 2ti minus 2j, and then 0k. And so now we're going to use our product rule. Okay, product rule says that the derivative with respect to t of r of t dot u of t is going to be equal to r of t dot u prime of t plus r prime of t dot u of t. And so at this point, we can just literally substitute and then evaluate. So r of t, remember, we go all the way back up, and r of t is 1 over t I minus j, and then plus ln of tk. And we're going to dot that. In fact, let me write this in the standard form, just to make it a little bit easier. So that's going to be 1 over t, comma, negative 1, comma, ln t, dotted with the derivative, which is 2t, comma, negative 2, comma, 0. And to that, we're going to add. So now we have r prime, which is going to be minus 1 over t squared, comma 0, comma 1 over t. And we're going to dot that with the original u, and the original u was t squared, comma negative 2t, comma 1. Right? So essentially what's going to happen is we're just going to get a big long expression. Right? So let's multiply these. So we're going to multiply 1 over t times 2t, and that's just going to give us 2. Negative 1 times negative 2 is a positive 2. And then ln t times 0, that's just going to be 0. All right, so the first one's nice and easy. Plus minus 1 over t squared times t squared, that's just going to be a negative 1. 0 times that 2t is just going to be 0. And then we have 1 over t times 1, which is 1 over t. And ultimately, this just winds up being 3 plus 1 over t for the dot product. Okay. All right, so in the next video, I'm going to show you how to take the derivative of a cross product, and then we can go through and start working on some integration from there.